Today our topic is energy stored in a magnetic field. When the current passing through a closed loop increases, the magnetic field in that loop also increases. According to Faraday's law, the time varying magnetic field induces an EMF. This back EMF opposes the current flow in the same loop. To maintain the current flow, the work is to be done by an external voltage source against the induced EMF. This work done is stored as the potential energy and which can be recovered when the current is turning off. This is the energy stored in a magnetic field. The first method is in terms of current flowing. Consider the work done in taking unit charge along a closed circuit once is equal to minus of induced EMF. That is, it is opposite to the induced EMF E. Then in that terms the work done can be written as W is equal to minus QE. Then if the current flowing is I, then the total work done per unit time can be written as dW by dt, which we explained as W is equal to minus of Q into induced EMF. So dW by dt equal to minus E dQ by dt is equal to minus E into I. That's equal to minus Li di by dt. As we know, induced EMF E can be written as L into di by dt. So, when the current passes from 0 to I, we can write the work done W is equal to integral 0 to I dW. That's equal to integral 0 to I Li into di. By integration, we can write the work done as half into Li square, which is the expression for energy stored in a magnetic field in terms of current flowing. Using this equation, we can derive the expression for energy stored in a magnetic field in terms of magnetic field. This one is energy stored in a magnetic field in terms of magnetic field itself. Consider a closed loop through which the current I passes. Then the magnetic flux in the loop is phi is equal to surface integral B dot ds, which can be written as surface integral del cross A dot ds, where we know B is equal to del cross A, and give it as equation number 1, where S is the surface bound by the closed loop. Now, applying the Stokes theorem to the RHS of the equation 1, then we get phi is equal to line integral A dot dl. We have phi is equal to closed integral A dot dl, and already we know phi is equal to Li. Then I am going to equate these two equations, that is Li is equal to closed integral A dot dl, and given it as equation number 2. We have already know W is equal to half Li square. That is given as equation number 3. Then substitute 2 in 3. Then we can write work done W is equal to half I into closed integral A dot dl. Or W can be written as half integral closed loop A dot I into dl. So, the direction from dl is interchanged with the current, as we know, where the current I flows in the direction of L as given in this figure. Then, from that equation, we can write for the volume distribution using similarity, where the volume current density is J. W can be written as 1 by 2 volume integral A dot J d tau, and consider this as equation number 4. Then we know Ampere's law, del cross B is equal to mu 0 J. From this, write J is equal to del cross B by mu 0. Then substituting this J in equation number 4, then we can write W is equal to 1 by 2 mu 0 volume integral A dot del cross B d tau. And in this equation, we can substitute a mathematical application. We know del dot A cross B is equal to B dot del cross A minus A dot del cross B. That is, del cross A can be written as B itself. So, equal to B dot B minus A dot del cross B. So, I have written after rearranging as A dot del cross B equal to B square minus del dot A cross B. So, from this mathematical substitution, I am going to substitute A dot del cross B in this equation. Then W is equal to 1 by 2 mu 0 volume integral B square d tau minus volume integral del dot A cross B d tau. When we consider the Gauss's divergence theorem on the second term, volume integral del dot A cross B d tau will be changed as surface integral A cross B dot ds. That is, this equation will be 1 by 2 mu 0 volume integral B square d tau minus surface integral A cross B dot ds. So, as we know, W is equal to integral A dot J d tau and also W is equal to this. So, we can write 1 by 2 integral A dot J d tau is equal to 1 by 2 mu 0 volume integral B square d tau minus surface integral A cross B dot ds. So, consider this as equation number 5. We have to study the physical term behind this equation. So, when we consider the LHS of this equation, when we integrate this for a whole space, the volume integration remains constant since the whole space remains contains the current distribution as a constant. So, when the RHS considered as the space increases, the volume integral increases and the surface integral decreases. In such a way, for the whole space, the volume integral will be maximum and the surface integral vanishes. So, the RHS will be 1 by 2 mu 0 volume integral B square d tau. If the integration is carried over all space, W is equal to 1 by 2 mu 0 integral all space B square d tau. So, the entire energy is stored in the magnetic field. The energy stored in a magnetic field can be written as W is equal to 1 by 2 mu 0 all integral B square d tau. From this, energy density in magnetic field can be written as B square by 2 mu 0 or is equal to 1 by 2 A dot J. So, we can compare the energy density and the work done in electric field and magnetic field. The energy density in electric field is equal to 1 by 2 V dot rho is equal to half epsilon 0 E square. And energy density in magnetic field is equal to 1 by 2 A dot J is equal to B square by 2 mu 0. And also the work done in electric field is equal to 1 by 2 volume integral epsilon 0 E square d tau. And magnetic field 1 by 2 mu 0 volume integral B square d tau. Thank you.